Professor Andrzeja Lasoty lecture will be today delivered by Professor Imkeller from Humboldt University. But before we start, I would like to ask Rector of the Silesian University, Professor Tomasz Pietrzykowski, to say a few words.
Thank you. Good afternoon. This is my great honor and pleasure to welcome all of you once again, this time on behalf of the Rector of the University, Professor Ryszard Koziołek, the whole academic community of the University of Silesia, and myself personally, to the 16th lecture, Andrzej Lasoty lecture, and above all to welcome our distinguished guest, Professor Imkeller. It's a real honor for us that you are here with us. The events like this one, cutting-edge science discussed by a group of people of different backgrounds, generations, but somehow united by a passionate love for knowledge, for truth, are in some sense the very essence of what university is. This is the point of why we are here. Everything else is to some extent secondary, derivative, technical, so to say. So I feel really privileged that we have colleagues at our university who are engaged enough to organize such a series of lectures like this one, and to let us meet personally and talk to such distinguished scholars, such creme de la creme of the world research in various disciplines. So please let me take also this opportunity to say that we as the university are really grateful to all of you, to those of you who participated in setting up this series, in organizing the today's event, and in taking part in everything related to the research activities that makes it possible for us to organize such meetings as today's lecture. I wish you a very interesting time here, and in particular, please let me also wish to Professor Imkeller to have a nice and interesting stay at our university. We're really grateful that you accepted our invitation, and I hand over.
Okay, thank you. And now I would like to invite the Dean of the Faculty of Science and Technology, Agnieszka Nowak-Brzezińska, also to open our event.
Thank you very much. Ladies and gentlemen, dear distinguished guests, on behalf of the Dean of the Faculty, Professor Danuta Stróż, I would like to warmly welcome everybody and this very great event which we try to regularly organize here at the University of Silesia and at the Faculty of Science and Technology. I think that we are all proud that such a great scientist as the Professor Andrzej Lasoty was represented our university. I would like to thank all the organizers, the members of the chapter of the lectures, the chapter in which the Professor Łukasz Stetner is the head of, but also other members. I would also like to thank the director of the institute, Professor Katarzyna Horbacz, who cannot unfortunately be with us today because of flu. So once again, as a dean, I am grateful for all organizers. I would like to thank Professor Imkeller for giving us a very interesting lecture, and I would like to wish everybody to have a great discussion after the lecture. And what else? I would like to officially open the 16th lecture of Professor Andrzej Lasoty. Thank you very much.
Okay, thank you. And now let me say a few words about Professor Lasoty lecture. Professor Lasoty passed away at the end of 2006, and then starting from 2008, a group of his former students and friends decided to organize his memorial lecture and it is organized every year, starting from 2008, and exceptionally we had one break, but the last year we had 2 lectures, just because of pandemic we had one break. Now the last year we had 2 lectures, and now we continue our tradition. And usually our tradition is that we have every 2 years we have a speaker outside of Poland, and then we have every 2 years we have a Polish speaker. And now today's speaker will be Professor Peter Imkeller. Let me say a few words about Professor Imkeller. Professor Imkeller was graduated from University of Munich, and then he got, after several positions, he got a permanent position at University Humboldt University in Berlin. Professor areas of interest is stochastic analysis, random dynamical systems, stochastic dynamics, stochastic climate models, control theory, and stochastic finance, rough paths analysis, and stochastic partial differential equations. Professor Imkeller is involved in a number of activities. He is an associate editor of a number of journals. Recently, since he retired at Humboldt University, recently he is involved in the work of German Foundation, and in particular he is organizing several activities in in Africa, in Ghana, now financed by German Foundation. Professor Imkeller had a number of PhD and postdoc under supervision, so he was and he is very active, and as you can see that he can present, and he will present his recent results, which are very interesting. And before we start with a lecture, let me say a few words about our program and organization information. So after a lecture, we are planning to have a catering outside, and then after catering, 30 minutes after lecture, we are planning to have, because there was a tradition, we are planning to have a piano concert. This time piano concert will be financed by private sponsors, and Professor Czaskalik is going to play here. And afterwards I shall give you a program of the lecture. But right now let's come to the lecture of Professor Imkeller. So first of all, I would like to give Professor Imkeller a certificate, special diploma. So Peter, here is your diploma. Here's a book about Andrzej Lasoty, so that you should know, should learn something about Professor Lasoty. And now, let me announce the lecture. The title is A Fourier Analysis Based on a New Look at Integration. And Peter, the floor is yours.
Thank you very much, Łukasz. Can everybody hear me? I was told the microphone is on now. In fact, I am honored to be here. I didn't have the privilege of meeting Professor Lasoty personally, as far as I can remember, but I only came very late to the area which he represented, random dynamical systems or ergodic theory, chaoticity in dynamical systems. I was introduced to this area by Ludwig Arnold in the late 90s, and when I was talking to Ludwig this Christmas on the phone, I mentioned it, and he has very fond memories of Professor Lasoty, so there is a connection, but I'm afraid not a direct one. Okay, the title is now longer than I had it on the announcement of this lecture. I think I called it simply A New Look at Integration or something. And this would be a better title from my perspective now. Because what I mean with integration is exactly what you all know about integration, which is from the first years of calculus. So you know integration of, you know, a little bit of measure theory, you know integration. And this is what I want to have a new look at from the perspective of stochastic analysis, of course, and for a reason that will become clear on the first slide. But let me first mention why I chose to change the title. It's now more technical. It sounds more technical. And I took the more technical form because I was afraid in the end that I would not touch the area that Professor Lasoty was standing for, namely random dynamical systems. And so I added a second part, which is about the geometry of rough functions. So we're talking about rough functions, and the geometry of rough functions can be tackled by means of dynamical systems. I promise you, if I have time in the second part of my talk, I will come to that topic, and so I will be closer to the topics of research of Professor Lasoty, but I will not do this on your cost. I mean, I will always look at you and see whether I lost you or not, and I will not speed up just in order to make it for the second part. So, in the first part, I'm talking about this integration thing. Now, where does it start? It starts at one of the main points of development of stochastic analysis of this century. Namely, you can say either heat equation, so if sigma is equal to 1 and B is equal to 0, we have the simple heat equation. Diffusion equations, and if the drift B is non-zero and sigma is also more general, depends on x, you are talking about a parabolic a differential equation, partial differential equation, which comes from continuum mechanics. So it's important to physicists, to chemists, to mathematicians. Continuum mechanics, and the breakthrough by Kolmogorov in the 40s of the last century was that he could formulate this partial differential equation from continuum mechanics as a part in a particle picture, looking at, so to speak, idealized particles and describe the motion of those idealized particles. The simplest particle motion would be the motion of Brownian motion. In case you have the heat equation, so in case sigma is 1 and B is 0, you would have the heat equation that would be solved by the Wiener process Brownian motion itself. Now, in general, if B is general, if sigma is general, you end up with the solution equation of a stochastic differential equation. And in this stochastic differential equation in red, I have the stochastic integral. Now, this is the so-called Ito integral, and it is a non-trivial one because the trajectories of those idealized particles introduced by Kolmogorov are very rough. So, for instance, the trajectories of the Brownian motion itself are only alpha Hölder continuous for alpha less than 1/2. So they are oscillating rather fast. And this is the case for all the solutions of those stochastic differential equations. But if you want to study them, you have to first of all understand this integral. So you have to understand the integral of something in which the integrator is something that oscillates very fast, that is very far from being of bounded variation. And in the bounded variation case, you can remember your courses in elementary calculus, and this is what I would start with. Now, to make this picture round, so the Ito integral could be understood as an operator-valued object, but trajectory by trajectory. it was only understood in the so-called rough path analysis introduced by Terry Lyons in the late 80s, and lately by regularity theory of Martin Heyer and others. So only in the last couple of decades we could really understand those integrals path by path. And I will present to you, in what I will do, an approach of this integral which is based on Fourier analysis and which has a very Polish flavor, as you will see. So, okay, now first of all, so what I want to understand is integration, what you know from analysis courses. So I have two functions, f and g, real valued, defined on the unit interval, let's say, and I want to integrate one with respect to the other. But they are rather rough. If they are not so rough, then you can end up in Riemann-Stieltjes theory. So if, for example, the g, which is the integrator here, has bounded variation, so it can be associated with a signed interval measure mg on the Borel sets of the unit interval, and then integration of f with respect to g just means integration of f with respect to this signed measure. Now, if you do integration by parts, you realize that you can switch the roles of integrand and integrator. So you do the integration by parts formula, and then you get an integral of g with respect to f, and then if f has a bounded variation, then you can play the same game, and you can understand the integral of g with respect to f as the integral of g with respect to this signed measure. Okay. So there is a trade-off between the regularity of f and g, as is seen in this integration by parts formula here. Quite generally, Young's integral says that if f is alpha Hölder, g is beta Hölder. I will talk about Hölder continuity on one of the next slides. And if the degrees alpha and beta are large enough, so if the sum of the two degrees is bigger than 1, then integral f with respect to g is defined. But if we are in the case of Brownian motion and of stochastic analysis, I told you we have to integrate basically by Wiener process, for instance, and Wiener process is only alpha Hölder continuous with respect to an alpha which is less than 1/2. And its integrants might be a Wiener process again, so it also has just regularity, alpha Hölder or beta Hölder regularity with beta less than 1/2. So if I add alpha and beta, then I get something which is less than 1/2, so we have a problem. So we have to get beyond Young's integral. And this is what I want to explain to you. We have an approach of rough path analysis. Rough path analysis, as I said, was initiated by Terry Lyons in the 80s. We call this approach para-controlled analysis. Para-controlled, I will explain that. It has a lot to do with Fourier analysis. So what we will do is we will view functions in terms of their Fourier series as sequences. And this is what I mean by the Polish flavor in that whole story. Here is the idea of our approach. So what I do is I take the Haar functions, comes on the next slide, the definition of the Haar functions. Schauder functions are the primitives of the Haar functions. And since the Haar functions are just, well, constant on different intervals, the integral functions will be Lipschitz continuous, and this is why f, so term by term, it's Lipschitz continuous. And g will be the same, so if I want to integrate f with respect to g, and I develop both functions into their Fourier series with respect to Haar-Schauder, then I will have to integrate, in the end, I will have to integrate one Schauder function with respect to another Schauder function, term by term. And since Schauder functions, as I said, are Lipschitz continuous, I can do this integral quite easily. Of course, then I will have to ask the question, does my series converge? I have a double series, and this is all about, this is what this whole theory is all about. Okay. So, here are the Haar functions, just as a reminder. Haar functions have two indices, P and M. P is the dyadic generation number, and M is the number of position of an interval inside the dyadic generation. To understand this, just look at the pictures. So here I put down the first generation, this is the second generation, this is the third generation. So here P is equal to 1, 2, 3. Okay? So for the first generation, for M, I have two possibilities. M equal 1 and M equal 2. So for the first function, I take on the first half of the interval from 0 to 1/2, I take to be positive, and on the second half, I take it to be negative. And the positivity constant and the negativity constant has to be chosen in such a way that the integral over the square of the function is 1. I want a complete orthonormal basis system with the Haar functions. So I have to choose the size 2 to the p over 2 in order to have on the whole interval of length 2 to the minus p to get the integral equal to 1. Okay? So this is what I have to choose. So in the second generation, the index M is always denoting the position inside the dyadic generation. So M equal 1 is the first interval, M equal 2 is the second interval in the first generation. So in the second generation, I have quarter intervals. For the first function, I have the first quarter interval. For the second function, the second quarter interval, then the third and the fourth. And then it doubles again. So I have 8 intervals, 1, 2, 3, 4, 5, 6, 7, 8. And on the first half of the interval, I always have a positive constant, 2 to the p over 2. And on the second half, I have the negative of it. So this is certainly a complete orthonormal system in L201. Now the Schauder functions. Here are the Schauder functions. So the Schauder functions are defined as the primitives of the Haar functions. So I just take a Haar function and take its primitive. So what do I get? If I go back to the first picture here, so on the first half of the interval from 0 to 1/2, I have a positive constant. On the second half, I have the negative of this positive constant on the first half. So how does my Schauder function have to look? So it increases linearly to the middle of the interval, and then it decreases on the second half of the interval, and it has to touch 0 again because, well, the two constants correspond to each other. One is the negative of the other, and the intervals have equal length. So this is the Schauder function of the first generation, the first Schauder function of the first generation, the second Schauder function of the first generation. And this picture is important because it shows you, well, what I will use in a minute, namely that the Schauder functions have disjoint supports in one generation. Yeah? So this is the second generation, so I have 4 functions here, and you can imagine how it goes on. Okay? So now, how to step from the functions to sequences given by the Fourier coefficients. Now imagine you have a function f which has a square integrable derivative, call it f dot. The first thing I do in order to get what I want is I develop f dot with respect to Haar functions. So what does that give me? So it gives me exactly what I have written here. So f dot of s is equal to this series here. Sum over all p, sum over all m, and then come the development coefficients hpm f dot, and then comes hpm of s. Okay? So this is my f dot of s. Now I integrate it in order to get f of t. I integrate it from 0 to t. So integral 0 to t f dot of s ds is the integral of this whole thing. And then, of course, I interchange integration with summation. I take the series out, and then I have the coefficients here, hpm f dot, and then instead of HPM of S ds, I get GPM of t. So this is the Harshaude series of the function f. I derived it in the case where f has a square integrable derivative, but in fact, if you look at the coefficients, HPM f dot, I call them also HPM df, because it can be written for any function f that is continuous. Because all I have to do in order to take these coefficients, so HPM f dot, what would it be? It would be the integral of HPM s of f dot on the first interval of constancy of HPM minus the integral on the second half of the constancy. Yeah? So if I take the integral of f dot over an interval, I'm getting the increment of f over the extremities of the interval. So I'm getting, what I get here is, so I get the integral from, so I take the lower end point of my M interval, I take it to T0 PM, the midpoint at which the Haar function changes its sign and it switches from positive to negative, I call it T1 PM, and the right end point of the interval I call T2 PM. So now, if I take my development coefficients, I get just the difference, so this is the size of the Haar function, square root of 2 to the p, and then I just have to take the difference of the increment over the first interval with the increment over the second interval, which is this double increment here. Yeah? So f of t1 pm minus f of t0 pm minus f of t2 pm minus f of t1 pm. So this is my coefficient. And you would certainly agree that I can write down this quantity if I have a derivative or not. I just have to have that f is continuous. And this is what it is. Now, a very important observation is how large are these development coefficients? Now, if I look at this interpretation of the development coefficients that I just got, I can easily derive this estimate. So the 2 to the p over 2, which is first here, comes from the square root of 2 to the p. It's just another writing. Now, where does the 2 to the minus p alpha come from? Now, what I do here is I take the individual increments over one half of the interval, second half of the interval. Let's just fix the first one. So I take f of t1 pm minus f of t0 pm, and I divide this quantity by the length of the interval over which I took the increment, power alpha. Okay? So the alpha Hölder norm of f will be given by f of t minus f of s divided by t minus s power alpha, and I take the sup over all s and t. Okay? This is the alpha Hölder norm. So here is the alpha Hölder norm. So I take the first increment, divide by the length of the interval power alpha, but then I can compensate by the length of the interval power alpha. Length of the interval was of the order of magnitude 2 to the minus p, so I get 2 to the minus p alpha. And as an upper estimate, the alpha Hölder norm. Okay? And for the second interval, I do the same. So this constant c here comprises those unessential things like two intervals and so on. It's an unessential constant. So you have the development coefficient less than 2 to the p over 2 minus alpha p and the alpha Hölder norm of f as a function. I will talk about sequence space Hölder norms also. Okay, now let me argue that this series that I have here has to converge at least in the space of alpha Hölder continuous functions. Okay, now let's fix an alpha Hölder continuous function, and I already said how I develop or how I estimate the coefficients here. So, now let's look again at the Schaude function. So I have a Schaude function, I have my Haar function HPM here. So on the first half of the interval, it's square root of 2 to the p. On the second half of the interval, it's minus square root of 2 to the p. Now I take the Schauder function. I integrate on the first half, I go up to the middle, and then I go down again to 0. Now, how high do I get? What is the infinity norm of my Schauder function? It's quite clear. I mean, the slope given by the quantity by which I have to multiply it due to the size of the Haar function is 2 to the p over 2. And then I integrate over the first half of the interval. The first half of the interval has length 2 to the minus p minus 1. So the integral alone gives me just an increase of 2 to the minus p minus 1 multiplied by the size of the Haar function, 2 to the p over 2 minus p, it's 2 to the minus p over 2 minus 1. So this is how big the Schauder function becomes. And on top of that, I recall the fact that Schauder functions of the same dyadic generation all have disjoint supports. So if I'm talking about the infinity norm of the sum of all the Schauder functions, or if I'm talking about the infinity norm of one individual Schauder function, it doesn't make a difference. So if I want to estimate the contribution of generation number p to my Haar-Schauder series, so let's just fix a p here, HPMDF, GPM, and try to estimate the contribution of that generation. Now for HPMDF, I already have an estimate. This was given here. So 2 to the p over 2 minus alpha. So I take this out. It's a supremum over all m. So it does not depend on m. So 2 to the p over 2 minus p alpha. And then I have the sum of the Schauder functions. But the sum of the Schauder functions has the same supremum norm as one individual Schauder function, and we just saw that it's 2 to the minus p over 2 minus 1. The minus 1 is not important. 2 to the p over 2 is the essential thing. So if I take 2 to the p over 2, I have the 2 to the minus p over 2, which comes from the Schauder functions, and I'm left with just 2 to the minus p alpha. As an estimate, 2 to the minus p alpha times the alpha Hölder norm, of course. So this is an estimate of the contribution of the pth dyadic generation to my Haar-Schauder expansion of the function f. Okay? So as I said, the contribution of the pth generation is of the order of magnitude 2 to the minus p alpha. Now this 2 to the minus p alpha is a geometric series. So if I have to sum over all generations bigger than, let's say, k, the remainder of the contribution of the series development, I'm getting 2 to the minus p times k, because it's a geometric series. So 2 to the minus, not pk, not alpha k, sorry. 2 to the minus alpha k if I sum over all contributions of generations up from k. Yeah? And f alpha stays here. So you see, the series converges, and I'm getting convergence in the space C alpha, which I consider as the closure of this space, the space of those finite developments with respect to the alpha Hölder norm. So in fact, I have convergence inside the space C alpha. C alpha is the space of alpha Hölder continuous functions. Okay, now we leave the area of complete orthonormal systems. Just for simplicity of notation, I blow up the Haar functions by the factor 2 to the p over 2. Since they already had the size 2 to the p over 2, I'm now talking about functions that take on the first half of the interval the value 2 to the p, and on the second half of the interval minus 2 to the p. Okay? And I also blow up the Schauder functions by 2 to the p over 2 so that they get infinity norm 1/2. Before they had infinity norm 2 to the minus p over 2 minus 1, now they get 1/2. as an infinity norm, if I blow them up by the factor 2 to the p over 2. Now here is my series development. I have to also modify it or understand it in the new language. So I want to write the HPM as chi PM, which is this blow up, and I want to write the GPM as phi PM, which is this blow up. So I have to compensate for the fact that I blew up twice by the factor 2 to the p over 2. I have to compensate by taking the 2 to the minus p here, yeah, in order to get the right coefficients. So if I estimate coefficients or development coefficients in terms of the modified Schauder and Haar and Schauder functions, I always have to multiply by 2 to the minus p chi pm here. But now see what this is. Chi pm, I said, is 2 to the p on the first half, minus 2 to the p on the second half. If I divide by 2 to the p, it's just the difference of two indicator functions. Yeah? It's the difference of the indicator function over the first half of the interval and the indicator function over the second half of the interval. So this is how I understand my coefficients in the modified Haar-Schauder system, and I call them FPM. Phi PM is the modified Schauder function. And if you write them up, then you see that, well, FPM just becomes this. Well, you remember before it was, it was here. It had this factor 2 to the p over 2, and now it's just the double difference here. Yeah? So Fp, I claim, is just a linear interpolation of f on the dyadic points up to generation p. The reason is the Schauder functions vanish on the boundary points. And this is why this has to be true. Okay. So, now let's formulate this in terms of Ciesielski's isomorphism. Ciesielski, I think, is still active. He's living in Gdansk, is that correct? Oh, he passed away? Oh. Already? Oh, I wasn't aware of that, sorry. So this is so in memory of Ciesielski. So my Hölder norm on the sequence space now, I take the Fourier coefficients in the modified system, multiply by 2 to the p alpha, and take the sup overall p and m. Now if I calculate this whole thing, so I have 2 to the p alpha, and if I take FPM in terms of HPM df, I realize that I just have to multiply by 2 to the minus p over 2, so that I get this as the supremum here. So I define this sequence-based Hölder norm by this quantity here. I interpreted it already by taking the old equations between HPM df and the FPM, and remembering this inequality here tells you that if I divide by 2 to the p alpha, if I multiply by 2 to the p alpha minus 1/2 here, I'm getting something which is equivalent to the alpha Hölder norm on the path space. So in fact, if I define sequence-based norm as this, I'm getting equivalence to the path space norm here, and this is exactly what is the main statement of Ciesielski's paper from '61. If I go from the space of alpha Hölder continuous functions to L infinity, I take f and map it onto the Fourier coefficients, modified, multiplied by 2 to the p alpha. I'm getting an isomorphism between function space and sequence space. And this is exactly what we use in order to define our integral, or to understand our integral. Back to integration. Now let us again assume that f is an alpha Hölder continuous function, g is a beta Hölder continuous function. I want to integrate f against g, as I said in the beginning. So now I have f developed by Haar-Schauder, by the modified Haar-Schauder expansion here. I have g expanded by the modified Haar-Schauder expansion here. So here is my integral of f with respect to g. I'm getting double sums over Pm and Qn. I have to sum, of course, independently. Here are the coefficients, Fpm, dQn. And then I have to integrate phi PMS d phi QNS. Now, phi QNS has a derivative, which is the modified Haar function. Okay. So here is what I have to understand. I want to understand these quantities as functions of t. And now that I'm already in this terminology of Haar-Schauder expansions, I will try to understand the function which I have to integrate here as a function of t by taking its Fourier coefficients with respect to another independent Haar-Schauder system. So I remember we have the coefficients, sorry, they are here. So the coefficients were here. So if I take the coefficients, I have to multiply by 2 to the minus order of the dyadic generation. So 2 to the minus I, chi ij, and then I want to investigate those coefficients, the coefficients of phi Pm, chi Qn. This is the point where it gets a little tedious, a little technical, but I will go back to normal terminology in a minute. I just want to give you an estimate of this quantity. Now there is f coefficients, the coefficients of f, the coefficients of g, and then there are these quantities which only depend on the choice of the Haar-Schauder system. So I want to understand how big they get as independent quantities that do not have anything to do with f and g. So here is the lemma. So I want to estimate the size of the coefficient with respect to chi ij, 2 to the minus I, as I said, of phi Pm chi Qn. And I claim this is less than or equal to 2 to the p plus q minus twice the supremum of the three orders of the three dyadic orders I, P, and Q. In case Q is equal to I get a so-called resonant inequality. The inequality becomes resonant, and this is one of the main problems of this whole calculus, to get away the resonances. To get away resonances, you usually have to renormalize. So you start getting into renormalization theory of regularity theory. I will tell you how we handle the resonance problem here. So first of all, let me explain this in just one drawing. So let us assume, we have different cases here, of course. Let us assume that I is the smallest of the three numbers. I is less than Q is less than P, so that the P intervals are the shortest, the Q intervals come second, and the I intervals are the longest. And as I said, 2 to the minus I, chi ij, is just the difference of two indicator functions. I'm taking the interval from t0 ij to t1 ij, so the first half of this I interval here, and well, I just have to, well, to say that here I have an indicator function. Yeah? So now the rest comes, phi Pm chi Qn. Chi Qn is here, so Q is the second largest, so I have a large Q interval and I have a rather small P interval. And for P, I have just the Schauder function. The Schauder function goes to level 1/2, as I said, the modified Schauder function, and the red Haar function, chi Qn, has the size 2 to the q after this blow up. So what do I get if I take the Fourier coefficient indicated here? I just have to take, so I'm on the second interval, so I have size 2 to the q, because I have to take absolute value, 2 to the q, and then I have to take the area of that interval, of that triangle, which is of the order of magnitude 2 to the minus p, because the p interval is of the order of magnitude 2 to the minus p long. So I'm getting 2 to the q minus p, which I can also write as 2 to the q plus p minus twice the supremum of the three indices. The supremum of the three indices was p, so I'm subtracting p here again, so I get 2 to the q minus p. Now, if you have other constellations, they are all as easy as this, or even easier. It's just a little tedious to go all through all of them. So in the end, you will end up with this estimate. Only in the resonant case, you get a worse estimate. Now comes the estimate in terms of the so-called Paley-Littlewood packages. Now, what do I call a Paley-Littlewood package? I have my Harshauder expansion of f here. And if I'm referring only to the pth generation, I call it delta pf, and delta pf is only the contribution of the pth dyadic generation to my Harshauder expansion. Okay? Only the contribution of the pth dyadic generation. SPF is called the sum overall of Paley-Littlewood packages. So this I will refer to as the pth Paley-Littlewood package. So if I take the sum overall Paley-Littlewood packages of order q less than p, I'm denoting this by SPF. I already said that in the sequence space, so where we take the supremum of 2 to the p alpha times fpm, which is the same as the supremum over p of the infinity norm of the delta pf, because delta pf infinity norm is just the supremum over m of the fpm here. Yeah? So this is what I said before. So this is the same as I said before. So f is in C alpha if and only if this is finite. And here is the inequality of the previous lemma. Just if I sum over Paley-Littlewood packages, that is if I sum overall m and overall n here. So the 2 to the minus 2 supremum I p q gets away, and I'm just having 2 to the minus 1 times I sub p sub q minus I plus p plus q times the infinity norms of f and g as an estimate for the ith package of the product of the pth package of f and the qth package of g. Only in the resonant case you get a worse estimate with a quantity with a factor which is 1 here. Yeah? So only in case q is equal to I, you get, in this resonant case, you get a worse estimate. So here is how I decompose my integral. So I have f and g, and I have f developed into Paley-Littlewood packages delta pf. So f is the sum over the Paley-Littlewood packages delta pf. G is the sum over the Paley-Littlewood packages delta qg, and I'm summing over p and q, and I have a d delta qg here, which interprets as the derivative of the Schauder function, of course, as I was explaining before. So now come the three main parts of this integral. So we have a total sum over p and q here. I decompose this sum into two pieces if I'm summing over p less than q here and over p bigger than or equal to q here. So now, in the next step, I'm leaving this first part, just writing it in a different way. So d delta qg is preserved, and the sum overall p less than q of delta pf is written as s q minus 1 f. Yeah? So I'm summing overall p less than q, so I'm getting sq minus 1 f here, yeah, by this summation. And then I have p equal q here, which is this green part. So this is the symmetric part. And then comes the part for p bigger than q, which is here. Now, why am I avoiding p equal q? The reason is resonances. Yeah? So for the resonances, I have to keep the Q away from F, at least by factor 1. So I have this quantity, I have this quantity, and I have the green quantity. So delta PFD, delta PG. Now I deal with the second quantity, the second blue quantity here, and I do integration by parts. So I take the differential over from this side, put it over delta PF here. So I write it as sum over Q instead of sum over P. So I write it as sum. Okay, I think I'm here, yeah? I'm interpreting this quantity. Sorry, not this one. So I'm interpreting this quantity. I sum over all Q, and I want to do integration by parts. So in the end, I'm getting a sum over all, where the delta QG is without a D, and the D goes over to SQ minus 1F. And what remains is the boundary term, which is just the sum over all Q, SQ minus 1F delta QG. Now here I have no resonances because I kept away with the Paley-Litwood packages of F by a degree 1 from the Paley-Litwood packages of G. I call this the Boni paraproduct of F and G. This is what brings me now to the para-controlled calculus. Okay, and this quantity here, if I, well, write it with Q, if I write it with P and equate it with that, then you will see that, so if I write this index as index Q, P instead of Q, you will see that you can compare it with this quantity so that you get this minus this, and this is the so-called antisymmetric Levy area. This is the antisymmetric Levy area, the worst term of the three that I'm getting. The second term is the symmetric part, which was here, in which I can write as, well, if I integrate once again, I can write it as such a thing here. And then comes the Boni paraproduct, which was here. So my integral has to be split into those three parts. And according to my inequalities for the Harshauder system that I derived from these different sketches that I gave before, we will see that the three parts here have very different regularity behavior. So let's start with the regularity behavior of the symmetric part, because here is where you see how easy it is to get these estimates. It's just a game with the degrees of the dyadic generations here. So if I want the infinity norm of delta IF, delta IG, so this is the ith Paley-Litwood package of F, the ith Paley-Litwood package of G. If I want the product of them to be estimated in the infinity norm, in the supremum norm, I'm getting less than or equal to the supremum norm of the first one, the supremum norm of the second one. And now you remember how the norm F alpha and G beta was defined. Here it is. So if I have the infinity norm delta PF, I have to multiply by 2 to the P alpha, take the supremum over P in order to get the alpha Hölder norm of F in the sequence space. So if I look at my quantity here, I have delta IF here. I have the luxury, I can afford the luxury of multiplying this by 2 to the I alpha, take the supremum over I, and still have an estimate by the alpha Hölder norm of F. But then I can compensate by 2 to the minus alpha I. And I can do the same for delta IG with respect to the beta norm. So I have an estimate of this quantity of this product here by 2 to the minus alpha plus beta I times the alpha Hölder norm of F and the beta Hölder norm of G. And this is summable in I. So on the other side, I can sum, and I can take an infinity. I can take the supremum norm over the products of the Harshauder, of the Paley-Litwood packages products of Paley-Litwood packages, which will be, well, the sum over them is what I'm having here. So I can sum in I, and I'm getting S of Fg in the alpha plus beta Hölder norm is less than, because here I can now multiply by 2 to the minus alpha plus beta I get it by less than a constant times the alpha Hölder norm of F times the beta Hölder norm of G. In the same way you can treat the bony para product, and you can also treat the Levy area. But in those two cases, of course you have to calculate a little bit more. In those two cases you see that you get different behavior. Here you can only estimate by the infinity norm of F, which is worse than the alpha Hölder norm of F and the beta Hölder norm of G. And here you can estimate by, in the alpha plus beta Hölder norm of the Levy area, with alpha Hölder norm of F, beta Hölder norm of G, but only if alpha plus beta is big enough. If it is not, you're in trouble. So, here is the theory of Young's integral. If we are in the case where the Levy area can be is continuous with respect to the alpha plus beta Hölder norm, in case alpha plus beta is bigger than 1. So if alpha plus beta is bigger than 1, F is alpha Hölder continuous, G is beta Hölder continuous, then the integral as the double sum of the corresponding integrals of the Paley-Litwood packages exists as an object in C beta, and the beta Hölder norm of integral of F with respect to G is bounded by something inessential times alpha Hölder norm of F, beta Hölder norm of G. If you subtract the bony para product, you can even improve the continuity to the alpha plus beta Hölder continuity. On the other side, you have the same expression here. But if alpha plus beta is not bigger than 1, we are in trouble. So what can you do if alpha is less than 1/2, beta is less than 1/2? So then we have to do what Massimiliano Gubinelli was calling controlled paths. We have to control the paths. We have to refer to an external path, X, whose Levy area we know, and that can be controlled, that for which our F can be controlled in the following way. So suppose we have an external path X in C alpha. So those paths X, the reference paths X, can be any paths of the stochastic process like Brownian motion or like any other well-known stochastic processes. For those, it is always known that the Levy area exists, almost surely. And for all those paths for which the Levy area exists, I can do this calculus. Yeah? So I'm referring to a path X in C alpha, which has a Levy area. Now, I call a function F para-controlled by X if the following is true. If I can, so to speak, define something like an approximative derivative of the function with respect to X, our reference function. So there is an Fx which is alpha Hölder continuous, such that if I subtract from F the para product of Fx of the supposed derivative with X, the para product of Fx with X, this whole thing is twice as continuous. So this is something that replaces differentiability, the differentiability property, into a vague theory, which is the theory that we are treating here. So f in dx is called controlled by x, and fx, the function to which I multiply f in the para product here and subtract it from f, is called the derivative of f with respect to x. This is the terminology of Massimiliano Gubinelli. And here we can define a norm fx alpha, so the alpha Hölder norm of f, plus the alpha Hölder norm of the derivative, plus the 2 alpha Hölder norm of the remainder. Now here comes the decisive observation. We were talking about Levy areas. Levy areas were the difficult object. Levy areas were only behaving well if alpha plus beta is bigger than 1. Now, suppose I subtract this product of derivative with x, a paraproduct of derivative with x from my f here, I'm getting something which is 2 alpha Hölder continuous. I claim the Levy area of this object with x is well defined. Why? Because this is 2 alpha Hölder continuous and this is alpha Hölder continuous. So if alpha is bigger than 1/3, 2 alpha plus alpha is bigger than 1, and I'm in business. So the Levy area is well defined. So if I subtract the derivative or the paraproduct of the derivative with x from my f and take the Levy area with x, everything is fine. So the only thing I have to understand is the Levy area of the paraproduct of the derivative with x and x. But this can be understood by a so-called commutator estimate, which is only, well, this is the only really difficult part in the whole analysis to derive this commutator relationship. You can show that the Levy area of the paraproduct with x commutes, so to speak, or if I take the difference with integral of x d Levy area of x with respect to x, then its 3 alpha Hölder norm is bounded by this. So we only have to suppose that the Levy area of x with respect to x exists, and as I said, all stochastic processes obey this rule for almost all trajectories, and for those trajectories I can do this analysis. So here is the main theorem. If I have alpha bigger than 1/3, so we are already much better than Brownian motion, or much rougher than Brownian motion. If we don't hit certain quantities, 1/2, 2/3, x is a C alpha function, f and g are the functions with respect to which I want to do my integration. And then I suppose that the Levy area exists. So as I said, trajectories of stochastic processes that are known to us fulfill this property. This can be shown separately. So this converges. Then I can say that the integral of SNF, so SNF is the sum of Paley-Litwood packages of f up to n. This is the sum of Paley-Litwood packages of g up to n. So this integral of SNF with respect to S and g is here. It converges in C alpha minus epsilon for all epsilon, and the limit is the integral of f with respect to g. We can even say that this integral of f with respect to g is again controlled by x, by our control function x, and has the derivative f times gx. And this is the derivative, this is the quantities that you have to estimate the integral of f with respect to g in. So it is there is fx alpha, gx alpha, x alpha again, x alpha square, and the Levy area. Okay, so this is the theory of paracontrolled calculus with respect to some function which possesses Levy area. Of course, I can suppose that my f or my g itself is x. Yeah, I can do that. I do not have something that comes from outside. Okay, so that was the part on integration. Now you have to tell me if I should go on and talk about something that is closer to Lasota's work? Do you want me to? Okay. So here is my second part. Now I want to interpret a Schauder expansion of a function as a random attractor of a dynamical system. This is more recent work. Now let us try to fix the ideas. So I'm talking about the so-called Takaki functions. What are Takaki functions? They are written in this way. C of x is sum over all k, gamma power k. Gamma is a roughness parameter, f of 2 to the kx. Now f, if I take f to be the distance function from the integers, then my first iterations of f with 2 to the kx here are these. So this is f of x. So the distance to the integers increases to 1/2 to the middle of the interval, and then it decreases again. Okay? And then I speed up by twice. I speed up, I'm getting this as f of 2x. As f of 2 to the 2x, I'm getting this. As f of 2 to the 3x, I'm getting this. So I'm getting always up to 1/2, but I'm speeding up the frequency with which I take the increments. Okay? How can I write this as a Schauder function? I claim 2 to the gamma power k of 2 to the kx is just the sum of the Schauder functions if the gamma is 2 to the minus 1/2. If it is 2 to the minus 1/2. So if I'm in the case of Brownian roughness, I'm just getting this. So I'm getting a Fourier, so if I write this sum over all k as a Schauder expansion, I'm doing something as if all the Haar coefficients were 1, and the Schauder coefficients are here. Okay, just to make sure that this is in fact an alpha-Hölder continuous function, let us, so this function C here is a alpha-Hölder continuous function. Let's suppose that x minus y is of the order of magnitude 2 to the minus k. And then I take, in order to estimate the increment of C between x and y, I'm taking the first k terms and estimate them by taking into account that the function f is Lipschitz. So the first k terms are estimated in taking into account the Lipschitzianity of my function f. The Lipschitz constant is 1. So I'm just taking the increments here multiplied by 2 to the L. So I'm getting gamma power L, 2 to the L times x minus y. So this 2 to the L times x minus y is an estimate of the increment. Yeah? And for the remainder, from k plus 1 on, again, x minus y is of the order of magnitude 2 to the minus k. From k plus 1 on, I'm just taking the boundedness of f, and I'm not taking into account variances in f at all, so I'm summing only over gamma power L. Now what is this? If I sum, so gamma is 2 to the minus alpha, let's say, 2 to the minus alpha. So I'm going to dyadic logarithmic scales here. Alpha corresponds to gamma in this way. So gamma is 2 to the minus alpha, so gamma L is 2 to the minus alpha L times 2 to the L. So it's 2 to the L times 1 minus alpha, and I have to sum from L equals 0 to k. This again is a geometric series which is of order of magnitude 2 to the k times 1 minus alpha. And then I have x minus y. And for the remainder, this is again a geometric series. So I have gamma power L 2 to the minus alpha power L, I sum from k plus 1 to infinity, I'm getting something of the order of magnitude 2 to the minus k alpha. Now x minus y was of the order of magnitude 2 to the minus k. So if I take x minus y power 1 minus alpha away from here, I'm compensating it with this quantity. So I'm left with x minus y power alpha, but here I already have x minus y power alpha. So in both terms I have x minus y power alpha. So in fact I have an alpha-Hölder continuous function. Okay? This is how it looks in the Brownian case. Alpha equal 1/2. So gamma equal 2 to the minus 1/2. This is logarithmic, dyadic logarithmic scale. I want to investigate the geometry of C, in particular its local time. That's not very important because I cannot dive into the details of that calculus so deeply in order to deal with that. But this is what the Takaki function in the case, Brownian roughness case looks. Now, remember how I formed this function. So each term, compared to the previous term, speeds up the speed with which I run through the parameter space by the factor 2. So if I step from term k to term k plus 1, I speed up the scale in which I run through the parameter space by the factor 2. Now, in order to investigate the geometry of those objects, what people have realized is that you can understand those curves, like the Takaki curve here, as the attractor of a random dynamical system if you put the whole dynamical, if you put your Takaki curve into a hyperbolic dynamical system in which one of the two motions is the speeding up of the parameter, the speeding up of parameter space by the factor 2 each time I take a new term. So if I want a hyperbolic dynamical system, I need one additional direction in which I multiply by the factor 1/2 if I want to be measure preserving. Yeah? I want a measure preserving dynamical system. If I have one direction in which a parameter moves by speeding up the factor by the factor 2, I need another direction in which I reduce the speed by the factor 1/2. This is the so-called, well, Baker transform in terms of dynamical systems. What a Baker does is he pushes the dough, and if he pushes it, he reduces its volume by the factor 1/2 in one direction. It has to blow up by the factor 2 in the other direction. So, and this is exactly what I do here. Let's understand the dynamical system first of all. So I'm on the unit interval in terms of the Takaki function. Let's understand the whole thing first on sequence space. So let's fix sequence space backward in time and sequence space forward in time, just sequences of zeros and ones, dyadic sequences. I write those sequences omega minus n for the first component, with n moving backward in time, and omega n with positive index for n moving forward in time. So on this space, I take the product sigma algebra, the product sigma field, and I take the infinite product of Bernoulli measures. So measure 1/2 on 0, measure 1/2 on 1 for each component, and then I take the product to have everything independent. This is the infinite product of Bernoulli measures, and this gives me a metric dynamical system. Omega as a space, F sigma algebra, nu as the invariant measure, measure preserving, and theta as a map which is measure preserving. So if I move by one coordinate forward in time, on this infinite product, doubly infinite product, I measure, since nu is the product measure on the whole real line, on the whole integers, I'm having something measure preserving. Okay? Now, how does that interpret our dynamical system? Our Takaki curve. First of all, I have to translate this two-dimensional infinite sequence space into the unit square. So what do? I take the components backward in time and I take the dyadic sum. So here is the dyadic sum. So I'm ending up in the unit interval. Here I take the dyadic sum but forward in time with the second part. And if I take the image measure of my infinite product measure of my Bernoulli measure with respect to this mapping, then I'm getting the two-dimensional Lebesgue measure on the unit square. The inverse, so if I go from the unit square back to the components, this will be the dyadic representation of components in 0, 1 square. One's backward in time, one's forward in time. Okay, so this is dyadic representation. Now, how does my theta map into the unit square? So I denote my quantities xi and x, denoting the two quantities in 0, 1 square. X was the old variable in which the Takaki curve moves, and xi is the new variable that I didn't have before, which was added in order to have hyperbolicity of the dynamical system. So if I take the inverse image of xi x, then I'm getting xi bar minus n, so backward in time, and x bar n forward in time. I call them xi bar minus n and x bar n, just to denote the components in the infinite products. So now if I take the Baker transform as being the image of my step one motion on the infinite product space, what do I get? So if I'm moving forward in time, b of xi x, then so here, so I take my omega and go to the next omega. This makes this quantity here be multiplied by a factor 2 because I'm adding backwards in time. Yeah? So I get 2 xi with b of b xi x in the first component, and in the second component, so if I'm moving with theta one step ahead, I'm getting I'm getting my omega 0 on the place where omega 1 was before. So I'm summing over omega n, but with a factor 1/2 on top, and with xi 0 bar with 1/2. So xi 0 bar times 1/2 plus x times 1/2. So this is the motion of x in the forward direction of the Baker transform. And in the backward direction, I'm just getting the opposite. I'm getting contraction in the first component and expansion in the second component. Now I want to make this story shorter because that gets me too detailed. So let us just try to understand what the definition of the Takaki curve is in terms of our dynamical system, of this dynamical system with a Baker transform. So remember what the Takaki curve was. So Takaki curve is here. So f of 2 to the power k x. Now what is 2 to the power k x? 2 to the power nx is just b2 minus n of xi x. Yeah? b2 minus n, b2 minus 1 in the x direction was 2x, so b2 minus 2 would be 4x, b2 minus n would be 2 to the nx. So here we are. So 2 to the nx, the f of 2 to the nx is just f of b2 minus n of psi x. So in terms of the Baker transform. So I have the sum gamma power n f of 2 to the f of b2 minus n of psi x. If I act with the Baker transform in the parameters, so if I take c of b2 psi x, I'm moving forward with one b2 psi x here, so I'm getting, instead of the b2 minus n, I'm getting b2 minus n plus 1 of psi x here. Yeah? But this just tells me that if I want to sum in n minus 1, if I call k n minus 1, then I'm getting the old thing just with the factor gamma, because gamma power n was here, and I'm only summing over gamma power n minus 1, k was n minus 1, so I'm getting an extra gamma here. This is the old object, and I'm getting an extra term, and this is why we have self-affinity here. Self-affinity. So we have something which is, so if I take my curve, after acting with the Baker transform, I'm getting the old curve without the action of the Baker transform, plus some smooth term, and a factor gamma here. So now I'm getting this dynamical system. I have gamma times c here, plus a smooth function f, is equal to c after the Baker transform. So if I define a dynamical system on the three-dimensional space, variables psi, x, and y. So the variable y is for this here, so gamma y. So f of b2 psi x plus gamma y, and the first two components just go over by the Baker transform. Then I can say this what I was expressing here. C after the Baker transform is just a smooth function plus gamma times c without the Baker transform. This translates into f of psi x c without the Baker transform is equal to Baker transform times c of b2. So this is stationarity in the definition of the compact random attractor. Okay, so this tells you that the dynamicals, that our Takaki curve can be understood as a random attractor of a random dynamical system on the basis of this Baker transformation. Okay, now I will shortcut the whole thing. What I was saying here, self-affinity. The big advantage that we have in stochastic analysis is that we know that our stochastic processes can be self-similar. Self-similarity would be something which tells you that C after a measure-preserving transformation is the same as some factor with C without the Baker transformation. So we have to take off this quantity here, which makes affinity here. Now, shortcut is, if you define the stable manifold of the dynamical system is a well-developed object. I cannot go into details here. Now, if you define the stable manifold, then you will be able to define increments or functions of psi and x by taking infinite sums over the whole integers, not just the positive integers, as in the definition of the Takaki curve, but over the whole integers. And then it turns out that the object G minus here, this object, is just increment. So the increments of this object are just the increments of C minus, so regularized by an integral of the stable manifold. And this object is self-similar. And this self-similarity, which was not seen before, then ultimately gives you properties like this. So you get Sinai-Bohn-Rel measure is absolutely continuous for a certain parameter range. The regularized Takaki curve has a square integrable local time for a certain parameter range. And maybe the most important, most interesting thing is that you can now, by means of this self-similarity relationship, you can calculate beta variations of the curve, of the Takaki curve. So if I take the beta variation of the Takaki curve, and beta is 1 over the Hurst coefficient was minus log 2 over log gamma over log 2. So if I take the beta variation of my Takaki curve, then I can show it exists by means of this by this self-similarity. I can show it exists, and it is given by some ergodic average over the other variable of the stable manifold. So stochastic calculus or individual trajectory calculus for the Takaki curve can be started at this point. You know that the quadratic variation exists if h is equal to 1/2, if h is equal to 2, yeah, beta is equal to 1/2. So quadratic variation exists, and then you can start stochastic analysis by Ito's formula, Tanaka's formula, and so on. That's new. That is only a couple of weeks old. I'm sorry I cannot go into details here. I just could allude to some of the results that are possible. Thank you very much for your attention.
Thanks. So this was a really very interesting talk. Let's start discussions. Do we have questions? Okay. Just so
I am thinking about possible application of your theory of integral. For example, it is possible to use it in numerical approximation of solutions of stochastic equation, or, for example, to have some limit theorems to go to diffusion process by approximating, for example, the diffusion process by some.
I think you can. I mean, what was investigated by Terry Lyons already about 10, 15 years ago was that, what did he call this? Triangulation or something like that. So he used his approach of rough path analysis in order to do numerical approximations of the solution of stochastic differential equations. This is exploited at a large pace nowadays. There is groups in Berlin, I think. I do not follow everything they do, but my point was more, so I wanted to explain something which has a different flavor in a very particular situation, the situation in which you want to integrate one function against one other function. So if you put it differently, what I was explaining, you have integral FdG. So what you want to do is to integrate with respect to time f times g dot. Now f times g dot is already a challenge to analysis because g dot is a distribution with negative regularity index. So how do you multiply distributions with negative regularity index? This is the story that we try to solve with this approach. So in fact, what we did in the main paper with Massimiliano Gubinelli and Nicolas Berkowski was to do a theory based on this dyadic considerations, dyadic interval considerations for getting the products of singular distributions, and then do regularization or renormalization in order to understand products, renormalized products of irregular distributions, and this way to solve stochastic partial differential equations in which you have distribution-valued objects. So, for instance, heat equation or stochastic heat equation in dimension higher than 1. That was not possible before. But this, so to speak, this interpretation of regularity theory brought results in this direction. So this is what we were ultimately up to, or what we were originally up to. So multiplication of singular distributions, which brought us into those Boni para products. So analysts have been thinking about that longer before, and probabilists became only aware of it decades later. And this was when this calculus was created. In the meantime, I think for numerical applications, Alliance's approach via the so-called signature function is the most used nowadays. Yeah. So the signature is, so to speak, the picture of an abstract distribution in an infinite product in a chaos decomposition, let's say. Yeah.
Okay. Any other questions, comments? So I have one or maybe two questions. First of all, so concerning the first part, you define pretty general integral, notion of integral, and can you apply this to integrals with respect to fractional Brownian motion?
Yes.
Yes, and then another question is that because you have this interpretation, so can you continue this using formulating Ito formula and in terms of your series? Because usually if you want to calculate, if you want to involve, let's say, stochastic calculus, so you need Ito formula, okay. You need further calculations.
So Ito formula has different terms. The terms in front of the equality sign I don't touch. The first term after the equality sign is a stochastic integral. This is what I explained. The second part is an integral, usually a regular integral with respect to quadratic variation. Mm-hmm. Now, quadratic variation has to be given from God in this calculus. Mm-hmm. You cannot just derive it from what I did in the first part of my talk. This thing here is the first instance that by using ergodic theory, you can get around the problem and get the quadratic variation by the same considerations. But this was not possible in general. So in general, you have to suppose that you have a subdivision of your parameter space for which the quadratic variation or a p-variation of any of the required kind exists, and then you can do your calculus. So it does not come with a calculus. Stochastic integral or integral and term of the quadratic variation is a different thing. Mm-hmm. But here, so via this trick with dynamical systems theory, via this self-similarity relationship for one trajectory, you can get around it and you can interpret the variation in terms of ergodic averages. That's all I can say at the moment. Usually, it has to come from God.
Yeah, but coming a little further than another step, what about if you consider, for example, integrals with respect to infinite dimensional cylindrical Brownian motion or any process of this kind? Because here it was rather important for you that you have a finite dimensional noise.
I had finite dimension. What I was explaining could be easily translated into d dimensions, but not for infinite dimensions. I don't know at the moment. I'm also not familiar with if somebody tried this.
Perhaps not.
I don't know.
Okay, other questions, comments? We don't have. So let's thank once again Professor Imkeller. And now I have a pleasure to inform that we have a 30 minutes break, and we have outside we have a catering, and those who would like to continue, so another point in our program is concert Professor Trzaskalik piano and Edyta Nowicka sopran. It's a concert Frédéric Chopin 1980, 1949. Here's a program. So those who would like to continue, you can pick up the program of concert. Now we have a 30 minutes break. you.